Now we want to talk about gravitational potential energy. And to introduce the topic, we're just going to look at the definition of potential energy and then plug in the Newtonian universal law of gravitation, right? So here we have F dot dr. And we're going to move our object from some position 1 to some final position 2. And notice, okay, that with this definition, only the difference in the radial position from the center of the object you're taking the potential energy of, say the Earth, is important, okay? So we can pull out the constants that the integral does not depend on, and of course the universal law of gravitation is negative g times m1 m2 over r squared, so we can pull all the constants out and we just leave the radial term inside the integral and we can integrate. And what we get is the integral of r to the negative 2 is going to be negative r to the negative 1, or negative 1 over r. And we're going to evaluate that between our 2 points, r1 and r2. And if I plug that in, this is of course negative r2 to the negative 1, or negative 1 over r2 minus negative 1 over r1. And what this turns into is, if I can make this a plus sign here, and this just turns into R1 minus R2, 1 over R1 minus 1 over R2. So the potential energy, and technically this is the change in potential energy, okay? Technically this is the change in potential energy between 2 points, right? So technically I should have the delta sign up here. And so if I want to evaluate the potential energy between 2 points, all I have to do is know how far away these 2 points are from the center of the Earth, say, and I can plug them into this formula. Now, we've already seen that the change in potential energy of lifting an object a height h above the surface of the Earth is just mgh. Are these two formula consistent, right? Are these two formula consistent? And that's what I want to show at this point, that we can recover mgh from this formula for heights that are not very far from the surface, okay? So I'm going to rewrite this formula, and let's look at it this way. Let's say that we have the Earth, and here's the radius of the Earth, and I want to lift an object from the surface to some small height h. All right, from the surface to some small height h. And I want to know, are these formula consistent? So RE, the radius of the Earth, is going to equal R1 in the formula that we just had, and R2 is going to equal RE plus H, right? And now I'm going to plug that into our formula here, and so we have delta U is equal to G M1 M2 over, or multiplied by the difference of 1 over RE minus 1 over RE plus H, right? This was R1, this was R2. And what happens at this point? Well, I have fractions with different denominators, so I need to get a common denominator. So I'm going to multiply this fraction by RE plus H. I'm going to multiply this fraction by RE. Well, RE plus H over RE plus H, and RE over RE. So if I do that, we get this. I'm going to multiply this by RE plus H over RE plus H, and that is still multiplied by RE from the denominator here. Let me clean that up a little bit. And this is going to be minus, multiply this by RE over RE, and now I have my common denominators. Right, now I have my common denominators. But look what happens. Here I have a compound fraction, Re plus Rh, so this is Re over Re plus H times Re, this is technically bracketed off, plus H over that, right? So here I have Re over Re plus H times Re, and that's exactly what I have here. So I can subtract those two terms and I get 0, and I'm just left with the term involving my H in the numerator. So this is equivalent to H over Re plus H times Re. Now, what was our assumption? Our assumption was that we're only lifting the object a very short distance above the Earth's surface. And if that's the case, then Re plus H is very approximately Re. And if that's the case, then this is Re times Re, or Re squared. And now we can see that we are essentially there, because remember the definition of G, little g, 9.8, was capital G times the mass of the Earth, and m1 should be the mass of the Earth, divided by the radius of the Earth squared. And so m2 is the mass of the object we're lifting, and that was the mass that appeared in mgh. So this is simply m times capital G times the mass of the Earth divided by the radius of the Earth squared, which is little g, times h. So for lifting things short distances above the Earth's surface, we can recover the formula mgh from the definition of gravitational potential energy. All right. Now, I want to show you one more thing involving gravitational potential energy, and that is where we define, typically, you're actually free to define the zero of potential energy anywhere you want. We typically define the zero of potential, in other words, where does the potential energy disappear? We typically define that at infinity. So, if I want to calculate the amount of potential energy that it takes to bring two objects, right, close together from an infinitely far distance, then R1 would be infinity, and R2 is the finite distance that I bring them to after some time interval. Okay? So if I look at the difference in potential energy, oops, this should be 1. Okay, and again, I'm going to let R1 be infinity, so my objects are infinitely far apart, and then I bring them to some distance R2 apart, all right? If that's the case, if R1 is infinity, then delta U is going to be G M1 M2 times 1 over infinity minus 1 over R2. And because R1 is infinity, I can drop my subscript on R2 now because it's just going to be some distance R. All right. If I have infinity as my initial point, then my final point, I don't necessarily need a subscript. So I'm going to drop my subscript here. And I'll make this a little bit better, infinity sign. 1 over infinity essentially is 0. Okay, we'll ignore the math behind that, but if you think about it, it makes sense. If I divide 1 by increasingly large numbers, I approach 0. All right, so for the moment, we'll do a little bit of hand waving and just say that 1 over infinity is 0. And if that's the case, then I have 0 minus 1 over r. And so what this essentially boils down to is negative g m1, m2 over r. So the change in potential energy, or the instantaneous potential energy at any given point, r, is given by this formula, and that's the formula that we typically use. We typically set, or by convention, set our 0 point at infinity, and we look at the amount of potential energy or the change in potential energy that the objects have between each other as we bring them to a finite distance, r. Right? And that is the most conventional formula for potential energy that we have. All right? So, in the next video, we will talk about escape speed.